So our next lesson is about impulse and momentum. So there are many situations in which force acting on an object is not constant but varies with time. So to describe how a time-varying force affects the motion of an object, we will introduce two new ideas. These are the impulse of a force and the linear momentum of an object. So these ideas will be used with Newton's second law of motion to produce an important result known as impulse momentum theorem. So definition of impulse. So the impulse of a force is the product of the average force, which is denoted as a vector force, and the time interval or change in time during which the force acts is given by impulse is equivalent to the product of average force and the time interval. So J vector is called impulse of a force. Force vector is the average force, and the change in time is the time interval during which the force acts. So impulse is a vector quantity and has the same direction as the average force. So the unit of impulse or SI unit is Newton second. So unit of force is Newton and unit of time interval is in seconds. So Newton second. So the definition of linear momentum is denoted as p vector of an object is the product of the object's mass and its velocity. So linear momentum is simply mass multiplied by velocity. So linear momentum is a vector quantity that points in the same direction as the velocity. So SI unit of linear momentum is kilogram meter per second. So unit of mass is in kilogram and the velocity is in meter per second. So impulse momentum theorem. So when a net average force acts on an object during a time interval, a change in time, the impulse of this force is equals to the change in momentum of the object. So by the definition, the impulse of this force. So force multiplied by time is simply impulse. So the impulse of this momentum will be equal to the change in momentum. So final minus initial. So F delta T is impulse and uh, final velocity multiplied by mass minus initial velocity. Mass is the change in momentum. So considering illustration 8.1. So a baseball, okay. So a baseball has a mass of 0.14 kilograms. So the baseball or the ball itself has an initial velocity of negative 38 meters per second as it approaches a bat. So we have chosen the direction of approach as the negative direction. Okay. The bat applies an average force that is much larger than the weight of the ball, and the ball departs from the bat with a final velocity of positive 58 meters per second. So determine the impulse applied by the bat, and for letter B, assuming that the time constant is 1.6 milliseconds, find the average force exerted on the ball by the bat. So what are the solution? Given is mass of the baseball 0.14, initial velocity negative 38 meters per second, and final velocity is positive 58 meters per second, and the change in time or time interval is 1.6 milliseconds. So the required is for letter A is the impulse applied to the ball, and for letter B the average force exerted on the ball by the bat. Okay, so for letter A, so according to impulse momentum theorem, the impulse applied to the ball is given by this formula. Recall that impulse is equivalent to the change in momentum. Okay, so substituting the values from the formula, mass, final, initial. So that is mass is 0.14 kilograms. Final velocity is 58 meters. Okay, positive. Then the mass of the baseball is 0.14 and initial velocity is negative 38 meters per second. So when computing for impulse, you need to indicate the sign of the uh, velocities. So for final velocity, given is positive, so that is also positive. Then for initial, negative 38 meters per second, so include the sign. Okay, and computing this, the impulse of the impulse applied, okay, to the ball by the bat is positive 13.44 kilograms per second. Okay, now for letter B, uh, average force applied. So now that the impulse is known, so this is the impulse. Okay, we can now compute for the average force provided the given has a time interval. Okay, so from this formula, impulse is equivalent to the product of force multiplied by time interval. Then using this formula computing for force, you can divide the whole equation by change of time or the time interval. So this will be eliminated. Okay, so force now will be equal to impulse all over time. So force is equal to impulse j, okay, j vector all over time interval. So impulse is given, okay, positive 13.14 kilograms, and time interval is 1.6 milliseconds. So substituting the values, we'll get uh, 13.44 kilogram meter per second, okay, divide by 1.6 milliseconds, and that gives you a positive 8,400 Newton force. So the force is positive, indicating that it points opposite to the velocity of the approaching ball. Okay, so for example, scenario, if this is the baseball bat, okay, and the baseball is approaching with an initial velocity, okay, so the direction is negative, okay, so that is pointing to the left, and the force, so tendency force applied to the ball will be on this direction. Also, the final velocity after the ball gets hits, okay, the ball now has a final velocity uh, of a positive to the right direction. Okay, so final velocity is positive, therefore force similar direction to the final velocity, that gives you a final positive value. So illustration number 2, during a storm, rain comes straight down with a velocity of initial velocity of negative 15 meters per second, okay, and hits the roof of a car perpendicularly as shown in the figure. Okay, so the mass of rain per second that strikes the car roof is 0.06 kilograms per second, assuming that the rain comes to rest upon striking the car. So okay, uh, giving you a final velocity of the raindrop to 0. Okay, So find the average force exerted by the rain on the roof. So initial velocity of the rain is given as negative 15, that is pointing down. Okay, so that is the negative direction. Okay, and upon uh, this upon touching the roof of the car, okay, the final velocity is 0. Okay, now the average force exerted by the rain on the roof, so that is the unknown. So the given mass of rain per second is 0.06 kilograms per second. Okay, initial velocity of the raindrop is negative 15 meters per second. Negative is pointing downward. Okay, and the final velocity upon touching the roof is 0. So the required is the average force exerted by the rain on the roof. Okay, so the average force needed is to reduce the rain's velocity from initial velocity of negative 15 meters per second to its final velocity, or at rest 0, is given by the formula uh, impulse and momentum theorem. So that is impulse is equivalent to change in momentum. Okay, so impulse by formula, that is force, average force multiplied by change of time. Okay, so since mass of the raindrop is not given, so we can simply factor out mass from this given equation. So that becomes mass multiplied by final velocity minus initial velocity. Okay, okay, as shown here. Okay, and dividing both sides by change of time, or the time interval. So average, this will be eliminated. Okay, and force will be left on the left side as given here. Okay, and factoring m from the above, from the equation, that gives you mass multiplied by final velocity minus initial velocity all over change or time interval. Okay, so that is the unit of mass per uh, time interval is kilogram per second. So this is its value. So kilogram per second. So that is substituting the value of mass of rain per second. Okay, mass is kilogram and time is second. So mass all over seconds. So that is giving that will give you 0.06 kilogram per second, and final velocity is 0. Okay, minus that is initial velocity negative 15. So negative of negative becomes positive. So 15 multiplied by 0.06, and the average force will be positive 0.9 newtons. So this is the force exerted uh, by the roof on the rain. Okay, so that's why it is positive. But then the question is, find the average force exerted by the rain on the roof. So this force is in the positive, or the upward direction. Okay, this is positive 0.9 newton. That is the force exerted by the roof on the rain. Okay, now so the roof exerts an upward force on each falling drop in order to bring it to rest. So according to the action reaction law, the force exerted by the rain also has a magnitude of 0.9 newtons. So this is the force exerted by the rain. Okay, but then the direction of the raindrop is going down. So therefore, the final answer, so therefore the force applied exerted by the rain to the roof on the roof is negative 0.9 newtons. So this will be the final answer. So the principle of conservation of linear momentum. So the total linear momentum of an isolated system remains constant, that is conserved. An isolated system is one for which the vector sum of average external forces acting on the system is zero. So the principle of conservation of linear momentum states that the total linear momentum of an isolated system remains constant. Okay, so that can be also written as you can see, this is final velocity 1, final velocity 2, okay, and initial velocity 2. So we can say that the final total linear momentum is equivalent to the initial total linear momentum. So this will be our formula. Okay, so momentum gives you for formula, uh, mass multiplied by velocity. Okay, so illustration 8.3. Okay, a freight train is being assembled in a switching yard as shown in figure 8.2. Shows two box cars. So before complete, okay, so these are the box cars. So boxcar 1, boxcar 2. Okay, car 1 has a mass of 65 times 10 to the 3 kilograms and moves at a velocity of uh, positive 8 0.8 meters per second. So it, okay, this one. So mass 1 is 65 kilograms and its velocity, initial velocity, is positive 0.8. That is moving to the right. Okay, then car 2 with a mass of 92 kilograms, 92,000 kilograms, and a velocity of initial velocity of 1.3, positive 1.3 meter per second. Similar direction, that is to the right, so that takes us positive. Overtakes car 1 and couples to it as shown in figure B. Okay, neglecting friction, find the common velocity of the cars after they become coupled. So tendency, car 2 is much faster than car 1. Okay, so then when it overtakes car 1, it comes to coupled. Okay, so leading it to a single uh, motion that gives you final velocity. So the question is, find the common velocity Pf. Okay, single entity. Okay, now the given mass of 1, 65,000 kilograms, initial velocity of car 1 is positive 8 0.8 meters per second. Mass of car 2 is 92,000 kilograms and its initial velocity is positive 1.3 meters per second. So the required is common velocity when they become coupled. Okay. Now, momentum conservation indicates that final total linear momentum is equivalent to initial total linear momentum. But then uh, this equation now becomes uh, singular final velocity because they became coupled. Okay, so therefore the formula becomes mass of 1 plus mass of 2 then multiplied by final velocity. Okay, and initial total linear momentum, this one and that one, they are not yet coupled. Okay, individual boxcars. Okay, now so from this equation you can solve for the final velocity by dividing both sides, okay, by mass 1 plus mass 2, okay, plus mass 2. Then final velocity will remain as shown here, and the equation for final velocity will be given as this one. So final velocity will be equal to the initial total linear momentum all over the total masses. Okay, substituting the given values, okay, mass 1 is 65,000 kilogram multiplied by its initial velocity of car 1, okay, 0.8 meters per second, plus 92,000, that is the mass of car 2, multiplied by its initial velocity of car 2 is 1.3 positive, okay, dividing the sum of the masses, which is 65,000 plus 92,000 kilograms, and computing, you have a final result of 1.9 meters per second. So this is the common velocity VF when the cars became or become coupled. So starting from rest, illustration 8.4. So starting from rest, okay, starting from rest, two skaters push off against each other on smooth level ice, where friction is negligible, as shown in figure 8.3. Okay, so two skaters before push off, they are at rest. Okay, and after push off, this becomes the illustration. So one is a woman with a mass of 54 kilograms, and one is a man which has a mass of 88 kilograms. Part B of the drawing, okay, shows that the woman moves away with a velocity of positive 2.5 meters per second. That direction is towards right, so that is positive. Okay, find the recoil velocity, final velocity of the man after push off. So as you can see on its direction, the final velocity of man is to the direction of left. So probably the value that we'll be getting here is a negative or minus, has a minus sign, okay, by inspection. So given mass of the woman, or mass 1, will be 54 kilograms and mass 2 88 kilograms, and final velocity 1, or final velocity of the woman, is positive 2.5 or 2.50 meters per second. So what is the recoil velocity VF2 of the man? So the question here is, what is their initial velocity? So the initial velocity is of the man and the woman is 0 because they are at rest. Okay, so the momentum conservation, okay, from the formula, so total linear momentum final will be equal to initial total linear momentum. Okay, so initial velocity of the woman and initial velocity of the man is equal to 0. So this value will be 0. Okay, so the total momentum of these skaters before they push off each other is 0 since they are at rest. Okay, so momentum conservation requires that the total momentum remains 0 after the skaters have separated, giving you this equation. So total momentum after pushing, okay, will be equal to total linear momentum before pushing, which is 0 because they are at rest. Okay, so substituting from this equation, okay, we can determine now the value of recoil velocity of the man, bf2, this one. Okay, from this formula, okay, we can transpose this equation to the other side. Okay, that gives us from positive becoming negative. Okay, then dividing both sides by mass 2, okay, giving us negative mass 1 velocity final of 1 all over mass 2, and substituting the values, okay, so that gives us mass of 1 or mass of woman is 54 kilograms, and its final velocity after push off is positive 2.5 meters per second divided by mass 2 or mass of the man, which is 88 kilograms, so that is negative. Okay, then simplifying this value, that gives us negative 1.48 meters per second. Okay, so the negative or minus sign indicates that the man moves to the left as shown in figure B of the drawing.